For most of human history, interstellar space was a distant idea. A silent ocean we could observe but never touch. That illusion ended the moment a strange point of light drifted into the view of our instruments. An object so faint and unremarkable that at first it seemed no different from the dust that forever drifts between the stars. But appearances, as the universe loves to remind us, can be deceptive. What astronomers would eventually call three-eye atlas began as a dim dot, nothing more than a technical curiosity on the margins of survey data. Yet within months, that same dot would become one of the most significant cosmic discoveries of the decade. No one expected what James Webb's infrared systems saw next. As the telescope locked onto the object with its signature precision, the faint point of light expanded, revealing an immense, shimmering structure far larger than even the most generous estimates. What we thought was a piece of cosmic gravel turned out to be a roaming fragment the size of a small world, a remnant from an unknown star system that somehow survived ejection into the interstellar void. In a universe where nearly everything is destroyed long before it reaches us, the survival of such a body was a revelation. The first anomaly came quickly. Traditionally, an object traveling between stars should carry with it the cold, quiet signature of ice and rock. Instead, Three-Eye Atlas radiated an unusual heat pattern, the kind seen in bodies with internal layering or trapped thermal pockets. Webb detected reflections that pulsed across the surface as though sunlight were glancing off steep cliffs of crystalline ice and metallic plains scarred by ancient violence. A natural comet should have sprouted a tail when approaching the sun, but instead the object shed its tail entirely, leaving behind a bare structure that resembled a planetary core more than a drifting ice ball. Data flowed in from ground-based telescopes and from NIRCam aboard Webb. Everything pointed to the same truth. This was no ordinary interstellar visitor. Its diameter stretched across hundreds of kilometers, far larger than Oumuamua, larger than Borisov, larger than anything humanity had ever seen arrive from beyond the sun's domain. The impossibility of that size forced scientists into a frantic scramble. A world that large should not have survived ejection. The gravitational violence required to rip such a body from its parent system would, by all statistical likelihood, have shredded it to dust long before it wandered into our cosmic neighborhood. And yet here it was, intact, silent, drifting closer. The initial hypothesis was almost poetic in its tragedy. Three-Eye Atlas might be the last remaining piece of a shattered dwarf planet, a core stripped of its mantle, flung from its home in a stellar catastrophe no one alive could ever witness. Spectral analysis strengthened that theory. Webb's instruments identified a mixture of ices, silicates, carbonaceous material, and metals, many of them in ratios unfamiliar to scientists trained on the chemistry of our own solar system. There were even hints of ammonia hydrates and organic compounds embedded within the ice layers, markers of internal heating or tidal forces once at work beneath its crust. The story grew stranger still. Heat distribution across the surface showed patches of crystalline ice, the type that forms only after cycles of warming and cooling. That meant this object had once been closer to a star, perhaps warm enough to maintain liquid water deep beneath its outer shell. A subsurface ocean, frozen in time, drifting between stars for millions of years. If that was true, then Three-Eye Atlas was not merely a relic. It was a fossil record of a world that once held warmth, pressure, chemistry, and the possibility of prebiotic complexity. As data continued to arrive, scientists began to piece together the object's distant past. The slow rotation rate, one full rotation every few days, combined with its remarkable solidity, suggested a monolithic structure, not a rubble pile like typical comets. It absorbed sunlight slowly, released heat sluggishly, and endured the harsh radiation of the interstellar medium with an indifference that only a stable, dense body could possess. In short, 3I Atlas was built to survive. Whether nature designed it that way, or it was the outcome of violent selection, the only fragment left standing after a planetary system tore itself apart remained an open question. Webb recorded faint jets erupting sporadically from the object's outer crust. These were not the normal, smooth jets of sublimating ice seen in comets. They were irregular, sharp, emerging from fractures that looked as though they had been carved by ancient tidal forces or collisions. Each jet provided a small clue. There was pressure trapped beneath the icy layers. Volatiles, gases, clathrates, materials that had been sealed away for eons, now slowly escaping as the object approached our star. But the jets were only half the story. When the heat pattern was mapped across its surface, scientists identified something even more unusual: localized hotspots, tiny regions warmer than the rest. These could only exist if internal heat had been stored for unimaginable lengths of time, or if slow chemical reactions still simmered beneath the surface. Most interstellar bodies are inert. This one was not. The deeper the analysis went, the more extraordinary the implications became. Every model pointed toward the same conclusion. 3I Atlas was not primitive. It was a leftover from a differentiated world, one with a molten core in its youth, with geological activity, with the potential for water cycling beneath ice. Its chemical fingerprint did not match anything in the solar system. Its isotopic ratios hinted at a star older, richer in metals, more intense in radiation. This fragment did not simply drift here. It carried with it the memory of a long-dead planetary system. The public reaction was nearly as dramatic as the scientific one. The idea that a planetary fossil larger than Manhattan, older than the sun, was gliding quietly through the solar system captured imaginations worldwide. To many, it became a symbol of time, of fragility, of the shared material heritage of the galaxy. Theories exploded across social media and news networks. Some asked whether an object so large and so perfectly preserved could truly be natural. Others wondered whether ancient civilizations might have studied it, or whether nature alone could create a traveler of such resilience. But in the labs and observatories, one truth became impossible to ignore. Every detail that emerged from Webb's instruments expanded the mystery rather than resolving it. 3I Atlas was a survivor from somewhere far beyond our reach, a messenger from a lost world, and a living record of cosmic upheaval. And it was still getting closer. As 3I Atlas drifted deeper into the inner solar system, the scientific community entered a phase of intense coordination. For the first time in history, space agencies across continents synchronized their telescopes, computers, and orbital models to study a single interstellar body with full collective focus. This was no longer just a discovery. It was a rare cosmic opportunity that might not come again for centuries. Every hour, new data poured in from Earth-based observatories, infrared arrays, and the James Webb Space Telescope, creating a layered map of the object's composition, structure, and behavior as it warmed under the distant touch of sunlight. The behavioral shift was immediate. As the object absorbed sunlight, its surface reacted in ways that defied expectations. Sublimation on typical comets creates broad plumes of vapor and dust, spreading out into a glowing tail that stretches across millions of kilometers. But 3I Atlas behaved differently. when volatiles erupted from beneath its fractured ice. The jets were local, sharp, and chemically rich, ejecting clusters of polycyclic aromatic hydrocarbons and nitriles, complex organics rarely seen in such abundance. This was the first time Webb had detected these precursors of amino acids on a visiting interstellar object. The finding triggered debates that spread like wildfire. Was this simply exotic chemistry from a foreign system, or did it hint at deeper processes once active within the object? With each rotation, the jets illuminated the scars of its ancient past. The surface revealed a history written in jagged terrain, plateaus of metallic ice, basins carved by violent impacts, and deep fissures where the crust had torn apart under unimaginable stresses. As thermal data accumulated, a picture began to form. This was once part of a world with layers, with internal heating, possibly with a mantle of warm ice above a subsurface sea. The hypothesis was bold but plausible. 3I Atlas might have belonged to a moon-like body, similar to Europa or Enceladus, but older than the Sun itself and forged in a star system with a very different chemical fingerprint. Then came the density shock. Researchers comparing its gravitational influence with its brightness realized that 3I Atlas was far denser than its icy exterior suggested. This was not a porous body of loosely bound material. It was a compact, cohesive fragment with a mass large enough to subtly perturb the trajectories of outer planet probes. His gravitational signature hinted at a rocky or metallic core wrapped in a thick shell of frozen volatiles, an architecture eerily similar to the icy moons in our own system. But here, in this alien survivor, the ratios of metals to ices and the distribution of elements across its crust bore no resemblance to anything within the Sun's neighborhood. The implications were staggering. If this fragment had once orbited a star with higher metallicity, if its parent world had experienced intense tidal heating or hydrothermal activity, then what drifted into our system was not just debris, it was a chemical archive from a region of the galaxy humanity had never touched. Every atom on its surface carried the story of nucleosynthesis from foreign stars, from supernovae long extinct, from stellar nurseries far more turbulent than the calm cloud that formed our own solar system. As this realization spread, scientists began constructing detailed simulations of the object's origin. One of the most compelling theories envisioned a young binary star system where gravitational chaos was the norm rather than the exception. In such systems, planetary bodies often wander into unstable resonances, especially when gas giants migrate inward and outward, stirring their neighborhood like a cosmic blender. A close stellar encounter, a passing star brushing too near, could have unleashed the violence required to rip apart moons, protoplanets, and entire ring systems. In the aftermath, surviving fragments would be scattered into interstellar exile. 3I Atlas, with its stable rotation and dense core, might have been one of the lucky ones, hurled into the void before its world was vaporized or consumed. That was the first hint of its possible birthplace. The second came from isotopic analysis of the dust escaping from its surface. Webb detected ratios of oxygen, carbon, and heavy metals that simply did not match any known objects in our solar system. The oxygen isotopes pointed to a star with greater mass and higher metallicity than the Sunday. The carbon signatures indicated cycles of heating and cooling under conditions foreign to our region of the galaxy. This fragment, in essence, was a message in a bottle, a geological sample from an inaccessible corner of the Milky Way, delivered by the random tides of gravity. Yet the scientific wonder was mirrored by a growing sense of existential awe. For the first time, humanity could touch, measure, and interpret matter from a world that predated Earth. It was like opening a time capsule sealed billions of years ago, its contents untouched by any biological contamination, its chemistry frozen in the moment of its last exposure to starlight. In laboratories worldwide, researchers ran models to estimate how often objects like this might traverse star systems. The results were sobering, because large interstellar fragments are so dark, so cold, and move so slowly against the backdrop of stars, most would remain invisible unless they passed extremely close. 3I Atlas might be the first of a vast, unseen population drifting between suns. Webb's continuous monitoring revealed that the object's surface responded to sunlight in strangely slow rhythms. Heat seeped into its crust and radiated back into space with a delay far longer than typical icy bodies. This heat retention aligned with the hypothesis of a dense interior structure. But what startled researchers was the discovery of localized warmth hotspots scattered across the surface like embers in a dying fire. Even at near absolute zero temperatures, something within the object was storing and redistributing heat. It was a tiny signal, but in planetary science, tiny signals can carry enormous meaning. Perhaps chemical reactions still flickered beneath the ice. Perhaps ancient hydrothermal pockets had frozen solid but retained their thermal memory. Or perhaps internal fractures trapped sunlight deep within, heating the ice from the inside. Each possibility carried weight. Each possibility implied a long-dead world still whispering traces of its past. As public fascination skyrocketed, some groups pushed the narrative further, insisting that no natural object could preserve such complexity for so long. They pointed to its stability, its mass, its improbable journey across the galactic plane. Was it truly just a fragment of a world? Or could ancient intelligence have studied it, modified it, or launched it long ago? Scientists dismissed the notion of technology, but even they admitted privately that the object's endurance bordered on miraculous. To survive millions of years in deep space without eroding into dust required extraordinary structure. Whether sculpted by natural forces or not, 3I Atlas remained an outlier, a survivor among survivors. As the object continued its approach, its influence on the scientific imagination deepened. Astrobiologists asked whether interstellar fragments like this could seed young systems with complex molecules, giving fledgling worlds a chemical head start. Cosmochemists saw in its isotopes a tool for mapping the galaxy's stellar history. Planetary scientists viewed it as a pristine record of catastrophic planetary formation. Philosophers and storytellers saw something more. Proof that the universe is not static, that worlds die and worlds travel, that matter itself is a great migratory force crossing the galaxy in silent waves. 3I Atlas was becoming more than an object. It was a symbol, a wandering relic of cosmic memory. And every kilometer it traveled toward the sun promised more revelations. As 3I Atlas approached the orbits of the outer planets, the full scale of the object's influence on the solar system became impossible to ignore. Even from hundreds of millions of kilometers away, the gravitational signature of the interstellar giant produced measurable perturbations in the trajectories of long-range probes. The data confirmed what many had suspected. The object's mass was extraordinary, far exceeding the estimates derived from its apparent brightness. It was darker, denser, and more ancient than anything the solar system had welcomed in recorded history. NASA, ESA, and several international observatories began developing global light curve models to understand how sunlight played across the object's fractured crust. Every rotation revealed a landscape that defied conventional classification stretches of gleaming crystalline ice layered beside plains of dark, carbon-rich material that absorbed nearly all incoming light. Rugged cliffs rose sharply from the surface, catching the faint sunlight and scattering it in shimmering arcs. Deep valleys, carved by forces long lost to time, appeared as dark scars, absorbing heat in slow pulses and releasing it in rhythms too stable to be random. This was a world frozen in the moment of its destruction. Each crater echoed an impact from an ancient ring system. Each fissure told the story of tidal stresses inflicted by a star that no longer existed. 3I Atlas was the last witness of a lost planetary system, carrying the geological wounds of its violent past across the cold depths of interstellar space. As scientists examined its structure further, they discovered minerals that should not exist on a simple icy fragment. Hydrated salts, crystalline ices formed at high pressures, and silicate grains fused at temperatures hotter than any comet could endure, all were present in measurable quantities. These compounds implied cycles of heating and cooling, hydrothermal interactions, and the existence of a primordial ocean beneath the crust before the object was torn away from its home. If these interpretations held true, then 3I Atlas once participated in geological processes strikingly similar to those that shaped the early Earth. The more we learn, the clearer it became that this object was not simply a visitor, but a messenger. It brought with it a chemical and geological biography of a distant star system, one that might have produced habitable environments long before our own. Its ice held memory. Its metals held history. Its subsurface layers preserved a record of the thermal and chemical gradients that once flowed through its core. Yet one question refused to fade. How could something so large have survived the journey? In the brutal emptiness between stars, cosmic rays and micrometeorites tear apart most objects within a few million years. But 3I Atlas showed minimal erosion. The leading theory proposed that as the object wandered, sublimation carved away its outer ices, while refreezing preserved a protective, ever-renewing crust. A self-healing shield of frost and dust may have wrapped the core in a blanket that absorbed impacts and radiation. Instead of degrading, the object adapted to the vacuum, creating a barrier strong enough to preserve its internal chemistry in near-perfect condition. Another puzzle emerged from its thermal behavior. Webb's instruments detected heat retention far beyond that of any known comet or asteroid. Instead of cooling rapidly after each rotation, the object radiated its stored heat slowly, as if insulated from within. Some scientists speculated that trapped remnants of hydrothermal activity might linger as pockets of warmth deep below the ice. Others posited that mechanical friction caused by frozen layers rubbing against each other as the object drifted through uneven gravitational fields could generate slow, persistent heat. Whatever the source, the warmth added depth to the idea that this was no simple relic, but a geological archive, still whispering stories from its past. The deeper the data went, the more profound the implications became. If this wandering fragment contained complex organics, traces of subsurface oceans, and isotopic fingerprints from a metal-rich stellar nursery, then the galaxy might be awash with similar travelers. Interstellar space might not be empty at all, but filled with the silent ruins of ancient worlds, fragments of planets, moons, and proto-worlds shattered in the early chaos of stellar evolution. These fragments, drifting across the Milky Way, could seed young forming systems with exotic elements, altering their chemistry and potentially shaping the emergence of life. Such a realization reframed humanity's understanding of cosmic interconnectedness. No longer were star systems isolated islands. They were part of a vast exchange of matter, chemistry, and possibility. Planetary boundaries were illusions. The building blocks of worlds wandered freely, crossing light years to become part of new storylines. 3i Atlas was proof of that cosmic circulation, a piece of geological scripture carved in ice and rock. Researchers began modeling scenarios in which objects like 3i Atlas passed through protostellar disks. Their simulations showed a dramatic effect. A single interstellar fragment could deliver heavy elements, complex organics, and rare isotopes into a young system, enriching the disk and influencing the types of planets that later formed. Some simulations suggested such encounters could trigger the birth of rocky planets by providing the solid seeds around which dust could accumulate. Others hinted that interstellar fragments might catalyze prebiotic chemistry, delivering the ingredients needed for life to ignite in far-flung systems. The idea was intoxicating. Life's building blocks might travel not just from planet to planet, but from star to star. And 3i Atlas, wandering silently across eons, might have been one of countless couriers carrying the chemical potential for biology. As the object moved closer to the sun, new phenomena emerged. The increased heat caused its surface to crack in slow motion, revealing layers of ancient material untouched since the moment of its ejection. Webb's spectral data captured fleeting traces of noble gases trapped for billions of years, now venting weakly into space. These gases offered the purest glimpse yet into the atmosphere of the world. The object once belonged to its thermal history, its volatile cycles, its internal pressure. For planetary scientists, this was a dream. It was as though the galaxy had delivered to Earth's doorstep a sample from a distant world without requiring a spacecraft to leave the solar system. The object became a natural interstellar probe, carrying information no mission could have retrieved. Philosophers and anthropologists joined the conversation, recognizing the object's cultural weight. Here was a fragment older than Earth, older than the sun, older than everything humanity had ever known. It had survived stellar births and deaths, crossed spiraling arms of the galaxy, and arrived in our time by nothing more than the random interplay of gravitational tides. Its presence forced a humbling truth. The universe is not shaped by our existence. We are merely witnesses to its immensity, observers catching a fleeting glimpse of a traveler whose story began long before our species learned to speak. As the world watched, plans began to emerge for future missions. Concepts for high-velocity interceptors appeared in scientific journals and space agency proposals. Engineers imagined spacecraft that could chase interstellar visitors, rendezvous with them, and extract samples before they vanished back into the darkness. The discovery of 3i Atlas had sparked an entirely new frontier of exploration, one that sought not distant exoplanets, but the relics drifting between stars. In the end, what 3i Atlas offered was perspective. It reminded us that worlds die, but their pieces endure. That space is not a void, but a bridge. That stars are not isolated, but participants in a galactic ecosystem where matter circulates endlessly, carrying secrets, chemistry, and potential across unimaginable distances. 3i Atlas continued its journey, moving silently on a path that would one day take it beyond the sun's reach. But for the brief time it passed through our neighborhood, it transformed what we thought possible. It was a messenger from a forgotten world, a fragment of cosmic memory, and a reminder that in the grand story of the universe, Earth is not the center, only one chapter among countless others drifting through the dark.